This video will cover the formation of acetals. Another way to think about the formation of acetals is it's an addition of alcohols to a ketone or aldehyde. This is a lot like a hydration of an aldehyde or ketone. The formation of acetals from a ketone or aldehyde is acid-catalyzed. The formation of an acetal from a ketone or an aldehyde goes through an intermediate that results from the addition of one equivalent of the alcohol to the aldehyde or ketone. This intermediate is called a hemiacetal, meaning half an acetal. The addition of a second equivalent of the alcohol produces the acetal. We will look at the mechanism for the formation of acetals in two steps. First, the formation of the hemiacetal, and then the formation of the acetal from the hemiacetal. The mechanism for hemiacetal formation is just like the hydrate formation mechanism we've discussed previously. Just like hydration, the formation of a hemiacetal can be carried out under acidic or basic conditions. First, let's consider the acid-catalyzed mechanism. If we treat a ketone or an aldehyde with an alcohol and a strong acid catalyst, it will produce the hemiacetal. Take a moment now and pause the video and see if you can write the mechanism for this transformation on your own. Now let's look at the mechanism together. Just like hydration, the first step of the acid-catalyzed mechanism is protonation of the carbonyl oxygen. This produces a resonance-stabilized cation. In the next step, the nucleophile, an alcohol in this case, attacks the carbocation. This produces the tetrahedral intermediate. In the final step, the tetrahedral intermediate is deprotonated to produce the neutral hemiacetal. Next, let's consider the base-catalyzed mechanism for hemiacetal formation. If we treat a ketone or an aldehyde with base and an alcohol, it will produce the hemiacetal. Take a moment and pause the video and see if you can write out the mechanism for this transformation on your own. Remember that it will look very similar to the base-catalyzed hydration of a ketone or an aldehyde. In the first step of this mechanism, the base will attack the electrophile. This produces the tetrahedral intermediate. In the final step, the tetrahedral intermediate is protonated to form the neutral hemiacetal. Next, let's look at the mechanism for the second step, the transformation of the hemiacetal into the acetal. The transformation of the hemiacetal into the acetal can only be carried out under acid catalysis. Let's look at the acid-catalyzed mechanism, and then we will consider why this cannot be carried out using base catalysis. When the hemiacetal is treated with an alcohol and the acid catalyst, we get the acetal product. Just like the first step of hemiacetal formation, the first step of acetal formation is protonation. We want to replace the hydroxyl group with the alcohol. Therefore, we want the hydroxyl group to leave, and so this is the group we protonate in order to make it a better leaving group. Once we make the better leaving group, it leaves, forming a carbocation. This carbocation is resonance stabilized. In the next step, the molecule of alcohol attacks the good electrophile. This forms the tetrahedral intermediate. In the final step, this tetrahedral intermediate is deprotonated. to form the neutral acetal product. Now, let's consider why this step, the transformation of the hemiacetal into the acetal, is not possible with base catalysis. If we treat the hemiacetal with base, the first step of this mechanism, just like the first step of the mechanism for formation of the hemiacetal, would have to be attack of the base. However, if the base attacks this carbon, kicking off this leaving group, that would force a hydroxide leaving group, which we know is a bad leaving group. And we know that an SN2 reaction will not occur with a very poor leaving group. Therefore, there will be no reaction if we treat the hemiacetal with strong base. In summary, the treatment of a ketone or an aldehyde with two equivalents of alcohol in the presence of an acid catalyst will produce the acetal. This is a condensation reaction, so it also produces two equivalents of water. This is important because this reaction, like most reactions, is in equilibrium, meaning that it's reversible. That means that Le Chatelier's principle applies. If we increase the concentrations of either of the reactants, it pushes the reaction towards the right. If we increase the concentrations of the products, it pushes the reaction back to the left. Therefore, if we want to favor formation of the acetal, we can increase the concentration of the alcohol. Additionally, removal of water from the reaction also favors the formation of the acetal. Conversely, if we increase the concentration of water or decrease the concentration of alcohol, we will favor the formation of the ketone or aldehyde. Instead of using two molecules of alcohol, we can instead use a diol, and this produces a cyclic acetal. For example, if we treat a ketone or an aldehyde with ethylene glycol under strong acidic conditions, we will produce the cyclic acetal, again with the loss of two molecules of water. The formation of cyclic acetals is more favorable than the formation of acyclic acetals. This is due to entropic reasons. In the case of the cyclic acetal formation, we see that the condensation involves two molecules, the ketone or aldehyde and the diol. The formation of the acyclic acetal involves the condensation of three molecules. Therefore, there's a greater loss of entropy in the formation of the acyclic acetal, making the formation of the cyclic acetal more entropically favorable because there is a smaller entropic loss. Cyclic acetals are very common in biochemistry, most commonly in carbohydrate chemistry. Let's look at an example. First, we will consider glucose, a monosaccharide. Glucose can either adopt a linear structure, like this, or in aqueous solution, it can adopt a cyclic structure. In aqueous solutions, these two structures are in equilibrium with one another. The cyclic structure is the hemiacetal of the linear structure. First, let's number the carbons in each of these structures. The same numbers will correspond in the hemiacetal structure. The oxygen that used to be the aldehyde is here, and the oxygen that used to be the alcohol is here. This hemiacetal results from the condensation between the aldehyde at carbon 1 and the alcohol on carbon 5. When monosaccharides condense to form disaccharides or larger carbohydrates, they form acetal structures. Let's consider the structure of cellobiose. This is a disaccharide made up of two glucose monosaccharides. This disaccharide contains both a hemiacetal and an acetal.